All right, let's dive into multiple regression. I love this statistical test. It's probably my favorite, all-time favorite statistical test. You make stock market predictions. A colleague of mine has used regression models to do this and done fairly well. Sports predictions, lots of the gambling odds, lots of the predictions about who would win the any sports contest are done using some kind of regression analysis. Not always. As it turns out, just interesting aside, soccer results are very hard to predict, even with good regression models, whereas basketball results are much easier to predict. If you're interested in sports, by the way, you've got to type in 538 and then sports predictions. All kinds of interesting probability models there on sports outcomes. Health predictions. So if you haven't ever done one of these, type in lifespan calculator. You'll fill in a bunch of variables. I liked this result, but I also noticed that that came attached with a little plug for pension. I was started to doubt the bias of the site. Maybe they're trying to get me to invest a little bit extra in some insurance. However, these models, if they're done well, are usually using multiple regression. You put in all your predictor variables, and then they put out your most likely predicted outcome, in this case, lifespan. This totally unrelated to health, but this is important to me because it's where I really saw the power of stats. This was in grad school, and I was starting to hear all these things about how stats are manipulated and is it even worth it? Why am I even learning all this stuff? And so I did this little test on this game called Settlers of Catan. I won't go into the details, but basically each column is a predictor variable, and this column right here is the outcome variable. If it's green, that means I won the game. So each of these rows is one time I played this online game, one round of the game. If it's green, I won the game. If it's white, I did not win the game. So I won roughly a third of them, which is what you would expect in a three-player game. But then I took this data, I ran it through a multiple regression model, got the findings, used the findings to adjust my strategies, and these were my next 24 games. Again, you can see a green here is a win, a white is a loss. So it wasn't perfect by any means, but it was a huge effect size. And seeing this real life outcome, even though it was something as silly as a game, sold me on regression and even stats in general, at least the potential for it when used correctly. This was an article I came across about high school sports. They had used regression to take the number of sports you played in high school and predict your future salary. And I wanted to do the same thing since I had a national data set. So I'm going to take you through that as my first example, and then I'll go through a more health-related example. So multiple regression is really just the same as linear regression, except you have more than one predictor for whatever outcome you're trying to predict. So here we're going to stick with that article. That article is focused on future salary as the outcome variable that we're trying to predict. We're going to stick with that, but I'm going to throw in a bunch of more predictor variables into our model. So I ran this. This is a national data set. They were high school students in 2002. They were actually sophomores in 2002. It was a representative sample of these sophomores. And then they collected data throughout the years, specifically in 2012, 10 years later, so they were now in their mid-20s, so they could ask things like salary. It was still early in their career, but we can at least get a sense of how some things might be connected. So the first thing you want to look at in a multiple regression output is this significance F over here. This is telling us the statistical significance of the model. And what we're looking for, as always, you can interpret it like a p-value. It really is just like a p-value to the extent that the lower it is, the more evidence against the null. 0.05 is our typical cutoff. The null hypothesis in this case would be even knowing all of these, the values on all of these variables for a person gives you absolutely no extra predictive power about their future salary. And because this is so low, I say it's low because this E negative 21 here means that decimal point is getting moved 21 places to the left. So this number is way, way, way below 0.05. So what that tells us is this model as a whole, knowing someone's information on these variables does give you predictive power about their future salary. So now we go and see, well, how much predictive power does it give you? This multiple R is the same as that correlation coefficient R from simple linear regression. The only difference here is it's kind of packing all these variables together in a single, we're going to call it the model, quote unquote, instead of just looking at it variable by variable. If we square that 0.10, we get our R squared and our adjusted R squared. Here's where I would go to look typically, the adjusted R squared. It's what we predict, how strong we predict the relationship or the model is working in the population. This can be converted to a percent. So this would be 1%. In other words, 1% of the variation in people's future salary can be predicted by knowing the information on these variables, which isn't a lot. To me, that effect size is pretty small. So it may be statistically significant, not too practically significant. The final thing I'd want to look at is the actual regression equation. And this is very similar to with one variable, but it does have the complication of having several extra variables in the model. So let's take a look at how to interpret that. So the intercept would say if you have a 0 on every variable here, you can kind of think of it as a baseline. This is what the predicted value would be. In this case, predicted salary. So a student that had a 0 on all of these would have a predicted salary of $21,400. So we start there. Everyone gets the intercept. Then you go through line by line and you take whatever your value is. You might as well do this for yourself, what you did in high school. If you never did cheerleading in high school, you would be a 0 here. If you did do cheerleading, sorry, you'd be a 1. You would then, you would then take that number, either 0 or 1, multiply it by this. You can think of it as the slope, and then add to this number. So if you did do cheerleading, you would be a 1. You would multiply 1 by negative 1,400. That would give you negative 1,400. You would add that to your base salary, predicted salary. You would now have a predicted salary of $20,000. In other words, by being in cheerleading, you now have a lower predicted salary. If you weren't in cheerleading, you'd have a 0 times this is just going to give you 0. Volunteering, in high school, you could have a 0. Less than once per week would be a 1. Once or twice a week would be a 2. Almost always would be a 3. You take whatever your value is, multiply it by this slope for volunteering, and then add it to whatever your current predicted salary is so far. So for me personally, I probably did once or twice a week. That would be a value of 2, 0, 1, 2, 3. 2 times this number would give me about $3,100. I wasn't a cheerleader, so I would add $3,100 to this, and I'd now have a predicted salary of $24,500. You continue to do this for all the variables, and you can get your predicted salary for your mid-20s if you're not already past your mid-20s. This is just, again, an R squared of 1%. It's really not a lot of predictive power based on knowing what you did in high school. One thing I want to point out, though, look at this. Playing softball, on average, lowers your predicted salary by almost $3,600. Playing baseball raises it by almost $3,900. What is up with that? So what's going on here probably has nothing to do with baseball and softball, or very little to do with that, and much more to do with what basically, are you male or female? This right here is the gender pay gap disguised. It's that lurking variable where gender is really the reason why these people are getting paid less, these people are getting paid more, but it's disguised as softball and baseball, because if you look at these variables, that's really the best way to tell if someone is a male or a female, is by knowing their answer to softball or especially if they did play softball, they're probably female. If they did play baseball in high school, they're probably male. Not all times by any means, but that's the way the gender pay gap is getting coded into these predicted numbers. So how would I use multiple regression? Well, first of all, I find something I care about, which is easy enough. One is teaching, one is my daughters. I find a problem, as you've probably heard in this course so far, sleeping has been an issue over the past years. And then I collect data. So I have to find a way of measuring. I could every morning when I wake up, I could rank my sleep on a scale of 1 to 10. That would be kind of shaky outcome. Maybe it would help me find some major variables if they existed. But I wanted to get a much more accurate measure, and that's why I used a Fitbit to measure my amount of deep sleep, total amount of sleep, amount in each of the sleep stages, things like that. I also wanted to measure a few variables that might be causing it, so I looked at screen time right before bed, when I started trying to sleep, what kind of noise was going on in terms of white noise, the amount of light, how many my girls, my stress level that day, all kinds of things, what I ate that day. And I measured those variables over the course of a longer period of time, basically until I lost my Fitbit, which is why we only see 24 rows on the spreadsheet I often share. And then I take a look at the output here. So again, the first thing I look at is significance F. P-value. This number is not below 0.05, so I do not have a statistically significant model. However, I'm still interested in looking in this data because it's my data. I'm really just looking for hints at what might be going on, so I'm okay if I'm not fully convinced that whatever it is a significant predictor. And I also am aware that I had a small sample size. Remember that the larger the sample size, that's naturally going to push that p-value down. Since I had a small sample size, I'm expecting this to be a little higher anyway. So not statistically significant, but I'm going ahead and looking here further. Especially when I see the fact that my multiple R is so high. I mean, that's a pretty high R value there, 0.75. And when we square that, we get 56%, 0.56, which would be 56%. In other words, 56% of the amount of sleep I'm getting per night can be predicted by the predictor variables I put in the model, which I'll show you in just a second. This again is much lower because I have such a small sample size. So it's telling me 26% in general, 56% in the nights I actually took data on, 26% if I want to be more broad in general predicting. And here, how do I interpret all this? I think I'm going to go ahead and do this in a separate video so I can just focus a little more individually here.